Okay, today we are going to study another very important element of the GLM family, and is the Poisson regression model. We have seen already the linear regression model, we have seen the logistic regression model. Another relevant member of the family is the Poisson regression model. Now, the Poisson distribution, the Poisson process is probably the most used distribution when you are dealing with counting. It's a counting process. It is used in scenarios where you are essentially counting the occurrence of certain event, and these events happen at a certain rate, but more than that, they are completely random. Suppose, for instance, you are studying earthquakes, and you know that in certain area you have more or less 2 earthquakes per decennia, per decade. But other than that, you have no further information. We don't know exactly when these earthquakes are going to happen, but we do know through historical data that we have more or less 2 events every 10 years. So the Poisson distribution was, as is obvious, was created through a French mathematician, Siméon Denis Poisson. It's a discrete probability distribution that gives you the probability that a given number of events may happen in a fixed time interval or in a fixed region of space. And the only thing we know is that these events happen at certain specific rate, and that they are independent from each other. But more than that, we do not know. For instance, let me give you a number of examples. The number of meteorites greater than 1 meter diameter that strike Earth in a year. I mean, there is some kind of average number of meteorites greater than 1 meter that strike Earth every year. Now, exactly on which moment these meteorites are going to strike Earth, that's unknown. What we know is that there is some average number of strikes per year, and we know that these are independent events. Or, for instance, the number of patients arriving in an emergency room between 10 and 11 p.m. in certain hospital. Again, we have some kind of idea about the average number of patients we get every Saturday between 10 and 11 p.m. in Vergallesa hospital here in Hasselt. But exactly at what time they are going to come, that is something that we do not know. Or, for instance, if you're talking about physics, the number of photons hitting the detector in a particular time interval. These are the type of situations where you may be interested in using the Poisson distribution. You want to quantify the probability that certain number of events will happen in a fixed interval in time or in a fixed region in space. And the only thing you know is the rate, the average with which these events happen. But more than that, and these events are of course independent, but more than that, you don't have any further information. So here you have, this is the Poisson distribution. Is a discrete, you have a discrete random variable y, and you're going to say that this random variable follows a Poisson distribution. If it has a support, of course, the natural numbers, including the 0, you may have 0 events, 1 event, 2 events, 3 events, etc. And the probability that you will have y events is given by this expression over here. That is basically the Poisson distribution. It is denoted in this way, and lambda, the parameter you have over here, is just the mean of the distribution. E is the Euler constant. You all know that is 2.7182, etc. And lambda is the mean number of events that happen at a given time interval or region in space. Now, the Poisson distribution has a very specific mathematical property, and is that the mean and the variance are the same. Now, this is a mathematical property of the distribution, but when you try to use the distribution in real life, it is frequently a problem, because real data frequently do not follow this specific pattern. Counting data do not always follow this specific pattern. Sometimes the mean and the variance are not the same. A phenomenon that you have very frequently is that the variance is actually larger than the mean, and then we talk about a problem called overdispersion. By the way, it can also happen with binary data, but we are going to see more about that later. Now, we saw when we were studying inference the law of the large numbers. Well, we also have in probability theory the law of the rare events. And essentially what that says is that you can approximate certain binomial distribution using a Poisson distribution. For instance, if you have an event that can happen with a very small probability, but you do have a lot of trials in which these events can happen, then the number of times that the event will happen, in principle, that follows a binomial distribution. You want to calculate the number of events. What is the chances that I will get k events in n trials? That is essentially a binomial distribution. Now, if n is very large, very, very large, and the probability of the event is very small, then you can approximate that binomial distribution with a Poisson distribution. And this is something that can be relevant in certain practical applications. So for example, suppose that you have a particular river and you know that catastrophic floods can occur once every 100 years. You are, in the Nile of Euphrates, one of these rivers, and you know that every century you may have really kind of a catastrophic event on average. Now, what is the probability that you will get, for instance, this catastrophic event, these catastrophic floods, that you will get 0, 1, 2, 3, 4, 5, 6 of these catastrophic events in a 100-year interval. Now, this is the typical situation in which the Poisson distribution is used. And as you may expect, so as an average, you have a one catastrophic event in 1 century. Well, what is the chance that you will get not catastrophic event at all in the next 100 years? Well, that is 0.37 approximately. The probability that you will get 1 is more or less similar to the one that you will get 0. And of course, this probability starts decreasing when you increase the number of events. So what is the probability that in the next 100 years you will get 6 times this catastrophic event? That probability is extremely small. So this is the type of situations in which the Poisson distribution may be of value. Now, let's see a little bit of a more realistic example. This is a study in skin cancer, and is a study of the non-melanoma skin cancer among Caucasians in 4 areas of the United States, and it essentially describes the number of cases of non-melanoma skin cancer among residents of 2 cities in each age category. So we have here 2 different cities. We have Minneapolis is given in this part of the data, and then we have Dallas, which is given here. And as you can see, what we have is the number of cancers in each city, but now divided by different age ranges. So for instance, in Minneapolis, there was 1 case in the category between 15 and 24 years. There was 102 cases in Minneapolis in the category of between 55 and 64 years. And what you have here, the N, is the number of individuals in that specific city within that specific age range. So that's the data set that we have. Now, what you want to do, of course, is you want to study the number of cases, and you want to see if there is an impact of city and age on the number of non-melanoma or skin cancer cases. So this is, again, a counting. We are counting the number of cases. It's not a normal distribution here. We don't have a continuous normally distributed random variable. It's not a binomial. It's a count. How we can model this type of data, how we can analyze this type of data. What we want to know here is if there is a difference between these 2 cities regarding the number of skin cancers. And is there a difference between the different age groups regarding the number of skin cancers? These are the questions we want to answer here. Now, the Poisson regression model, you can write it like all nonlinear regression models in this way. So we have seen that before. You have here the response, and you decompose the response as the expected value given the covariates plus some error term. Now, this mean response over here is assumed, as always, to be a function of certain predictors. In our case study, these predictors are city and age. Now, we will use the notation, the following notation for the mean, just mu, and now x comma beta, because this means may depend of certain covariates, a vector of covariates, and of course, parameters. And we will call that the response function. We have seen that the response function is the function that link the mean with the covariance. The link function is the function that links the linear predictor with the mean. They are in opposite direction. So we know that the Poisson distribution is the distribution of counts, so the mean has to be positive. And so the most widely used response function is just the exponential function, because this over here is going to be always positive irrespectively of the covariance and the coefficients we use here. It's the same case, the same reason why we use the logic link of the speed function as a response function and not, for instance, the linear link. So it's because you need to guarantee that the mean stays in the appropriate range. So like before, like with logistic regression, like with linear regression, in the Poisson regression model consists of two fundamental parts. You have the systematic part and you have the distribution part. What is the systematic part? There you specify the relationship between the mean, in this case the mean count, and your linear predictors. You are trying to model the systematic part of this phenomena. You are trying to see how the mean varies with the linear predictor. And then, of course, the observations are not all equal to the mean, so you also need a distribution part. And this distribution essentially tells you how these counts are going to move around the mean you specify in the first step. Now, like I said, like for logistic regression, you need to make sure that the systematic part does not create impossible values for lambda. Lambda is the mean count, is the average of countings. So it has to be positive. And that means that you need to use some kind of link function that allows you to keep this mean of this average count in an appropriate range. And in the case of Poisson, like with logistic, you may use different link functions or equivalently different response functions. But in the Poisson, the most widely used link function is then the logarithm. So the logarithm of the mean, this is the Neperian logarithm. The logarithm of the mean is equal to the linear predictor, or if you want to see it in terms of the response function, then it's just the inverse. So the mean of the Poisson distribution is equal to e to the power the linear predictor. So typically we work with this link over here. That is the systematic part. The systematic part tells us how the mean changes with the linear predictor. And the distribution part is going to tell us how now these observations vary, move around the mean, and we are dealing with a counting process. So the normal, the natural distribution to consider here is the Poisson distribution with parameter lambda. And what is the interpretation of the coefficient of this model? When we were dealing with the logistic regression, well, we saw that if you use the logic link, then the coefficients can be interpreted in terms of odd ratios or adjusted odd ratios because you have covariance in your model. What would be the interpretation of the coefficients here in the Poisson regression model? And well, let's just write the mean as a function of the covariance. Here we have the mean, this is lambda essentially. And what we have here is, well, we use the exponent of the linear predictor. That's our response function. Here we have our linear predictor. So what is the interpretation of these coefficients? Well, first notice that the exponent of beta 0, we have here the intercept in our model. What would be the exponent of beta 0? Well, that would be the expected number of counts for subject with all covariance equal to 0. If you make all the covariance over here equal to 0, this is what you have left. So that will be the mean response for subject with all covariance equal to 0. Please keep in mind, like with all other models, that it may not make a lot of sense to consider all covariance equal to 0. So the intercept needs to be always, you need to interpret it with care, unless you center the covariance. If you center the covariance, then will be the mean, the average count for subject which has all covariance equal to the mean. That in that case, the interpretation will be easier. Okay, that's for the intercept. What about the other coefficients like beta 1 or like beta 2? Well, the exponent of beta I is one of these coefficients, is called the relative risk. Is the risk relative to some baseline. For instance, suppose that you have a continuous covariant, xi. what that exponent means? Well, an increase of 1 unit in fxi. So if you move, for instance, from h to h plus 1, that has a multiplicative effect equal to the exponent of beta I on the mean of y. So keeping all the other covariates fixed, if you increase age by 1 year, let's say that x1 is age. So if you keep all the other covariates the same and you increase the age by 1 year, then the average number of counts is going to be increased by the exponent of beta 1. That would be the interpretation. What if you have a categorical variable? If xi is not continuous but categorical, then what the interpretation will be as follows. The mean of individuals in group xi is equal to the exponent of beta I, the mean of individuals in the reference group, keeping all the other covariates the same. So when you have a categorical variable, we assume that you have introduced dummy variables. You have this dummy variable xi here, and that essentially means that the average number of counts defined by this dummy variable, the group that this dummy variable identifies, is going to be e to the exponent of beta, is going to be the exponent of beta 1 times the number, the average number of counts in the reference group. So the interpretation is straightforward, and this is called the relative risk. How much you increase the risk is the way it is interpreted. Well, we have written our model. We have written the systematic part. We have modeled the average number of counts as a function of our linear predictor. We have done that by using a link function or a response function. In Poisson models, typically we use the logarithm of the mean, and that's what that's the link, the logarithm. That's why sometimes called log linear models, because on the log scale they becomes linear. So Poisson regression and log linear models are actually the same thing. So this is the systematic part. The logarithm of the mean is equal to the linear predictor, and then you model the distribution part just using a Poisson distribution. We have our model, we have the interpretation of the coefficients in the models, how we can now estimate the coefficients. And we go back to the first couple of lectures about inference. We are going to use again the maximum likelihood method. Now, suppose that you have n observations in your data. This is your vector of predictors. And here is the number of counts. You have n independent observations. Then the likelihood of your data, well, we know what it is. The likelihood is the probability of the data, of the density of the data. That's the likelihood. But you look at it now not as a density or as a probability, but you look at it as a function of the parameters, as a mathematical function. That's the likelihood. And the maximum likelihood procedure proposed by Fisher essentially says that, well, try to find the value of the parameters that make your data more likely, that make your data more probable. And each of these observations, y1 to yn, has or follows a Poisson distribution. So you just make the product of all these Poisson distributions. And this is what you have here, the product, because they are independent. That's one of the assumptions. So here I have my likelihood, and now I have to look at it as a function of beta. And we need to maximize this as a function of beta. So it's now a pure mathematical problem. The likelihood typically involves a product, and that's difficult to handle mathematically. That's the reason why we don't work with the likelihood per se, but with the log likelihood, which is just the logarithm of the likelihood. Why? Because logarithms, they have a nice property. If you get a product, they transformed this product into a sum. And it's a lot easier to work with a sum than to work with a product. So here you have the expression for the log likelihood when you use the logarithmic link in the Poisson model. And essentially, this is just proportional to this, because this term over here doesn't depend on beta, so you can forget about it if you want to maximize the log likelihood as a function of beta. So you can just work with this part over here. And how you maximize the log likelihood? Well, how you maximize a mathematical function? You calculate the stationary points. They are called the stationary points. These are the roots of the score equations. You calculate the derivative of that function with respect to the parameters. You equal that to 0, and you find the solution. There, among that solutions, among that group of solutions, you will have your maximum. You still need to check that it's a maximum or not a minimum, But for that we use the Hessian. And when you calculate the derivatives of the low likelihood with respect to beta, you get this very simple, elegant expression here, and you have to solve this equation now in beta. So you need to find the values of beta that satisfy this equation. Now you can write this also using matrices. So the score equations are again the transpose of the design matrix then times your vector of response minus the vectors of means. And now here the means of course are given by the exponent of the linear predictor because this is a Poisson distribution. So as you can see, the form of the score equations is again the same as we got it for the linear regression model or for the logistic regression model. The structure of the equation is always the same. What changed obviously is the mean here. If you are dealing with linear regression, that means is x times beta. If you are dealing with logistic regression, that is the speed function of your linear predictor. Here is the exponent of your linear predictor. But the equation is the same. And that's the reason why we can just put all these models, we can embed all these models within one single family, the GLM family. But we are going to discuss more about that in the next lecture. Now, as you can see, and unlike in linear regression, that's the only case, there is not a closed form solution. You cannot get the beta as a function of the other elements in the equation, like we did, for instance, in linear regression. Here you cannot. So you need to resort to numerical methods like Newton-Raphson, Fisher scoring, iterative least squares, etc. Now, what you have here is that the minus the low likelihood is a convex function. And that means that you can use all these procedures we just mentioned to try to find the solutions of the question. So here we have our model, we have the interpretation of the coefficients, and we have a procedure to estimate the parameters in the model. And is what I told you in the first two lectures. Once you understand all this inference methodology, once you understand what the likelihood is, the maximum likelihood is, and this holy trinity that we studied, the wall test, the likelihood ratio test, the score test. Once you start this, you can understand this at a level of generality, then is just the rest is just an application of it. So here again, we can just use the wall test, the score test, the likelihood ratio test, just if you want to assess that the parameters are zero or are in, you want to compare two models. All the theory we saw in the first two lectures is also valid here. What about model building? Well, as for logistic regression, in Poisson regression, there is nothing new. If you want to compare two models and these models are nested, you can use, for instance, the likelihood ratio test of the wall test, the score test. If you want to compare models that are not nested, you can use, for instance, the Kuiper information criterion. But all the discussion we had already about model selection, about model construction, can be, of course, extended to the Poisson regression as well. Now, model checking, the same thing. Everything we saw, you can use again here the deviance residuals. You can use again here the Pearson residuals, appropriately adapted, of course, because you have a different distribution, but generically, you can use the same thing. You can use the deviance test, you can use the chi-square test, the same thing, the same residuals, the same test. The only one you cannot use here, of course, is the Hosmer-Lemshow, because this is a test that was specifically designed for binary data. But the other tests, the other residuals can be used in the same way. You can construct more or less the same type of diagnostic plots. You can do the same type of analysis. Now, a problem that happens very frequently in Poisson regression is the problem of overdispersion. The data show more variability than what the model predicts. And that's why this is a problem that we are going to study with certain detail. You can also have underdispersion when the data, the variance is smaller than the mean. When the data show less variability than what the model predicts, that is possible, but in real life, overdispersion happens a lot more frequently than underdispersion. Underdispersion is more like a rare thing in application, but it can happen, and you can use also some of the techniques we are going to see today when you have underdispersion. Now, there is another issue that we need to take into account in Poisson regression. And that issue is that the window, as I told you before, the Poisson distribution, you try to model the number of events that happen in a fixed time interval or in a fixed region of a space. So you have a window in which you count the events. Now, if you look at this data for the skin cancer problem, you realize immediately that you need to be careful here. Because suppose, for instance, that you are looking at the number of skin cancers in Minneapolis in the group between 35 and 44 years old. Well, we observed there 30 cases of skin cancer. If you look at Dallas, in the same age group between 35 and 44, you had, well, 119 cases of skin cancers. So you can immediately think, oh, you have much more cases in Dallas than in Minneapolis in the same age group. But here comes the issue. You need to be careful because actually you also have a lot more people in that age category in Dallas than in Minneapolis. And somehow you need to take that into account. Now, how do you do that? Well, you do that by not looking at the mean as such, but looking at the rate. And this is relevant because, for instance, you may have, for instance, this case because you have these two cities, and in that age group, the population is not the same. Another possibility, for instance, is when you follow individuals a different amount of time. For instance, if you have six cases in 1 year, that should not amount to the same as if you have 6 cases in 10 years. So sometimes you need to readjust what you are doing and not modeling the average per se, but the rate itself. So the way to do that is that you don't model the mean as a function of the linear predictors, but the mean divided by the exposure. So you will model not only that there were 60 years or 30 cases, but that divided by the window you're using. And that can be, for instance, time interval, can be a certain area in a space, can be, for instance, a population in a city. And that's the way that you account for this problem. Now, in the Poisson regression, well, you handle by this way. You don't write your model in terms of the mean, but in terms of the mean divided by the exposure. So if you have as an average 6 cases per year, and you have in another as an average 6 cases every 10 years, you need to adjust by that time difference. And that's why you will divide by the exposure. And well, if you apply just these very basic properties of the logarithm, then you model the mean now not as the linear predictor, but as the linear predictor plus the logarithm of the exposure. And that extra term you get here is called an offset, because you don't need to estimate that term. That is a constant that is in the model, and you don't need to estimate any parameter there or anything. It's just called an offset. And you give that in R by just putting here this command. When you use the GLM, you put the offset command, and you give here the logarithm of the exposure. And by that, you make sure that you're taking into account that this city, for instance, in each age group may have a different number of individuals. So you cannot compare immediately this 30 with this 119, because these are counts coming from different sizes. One is coming from 9,000, the other one is coming from 100,000. You need to take that into account. Okay, let's fit the data. Let's see what type of answers we can get here. So here you use the GLM function, which is the function that we use for generalized linear models in general, and you want to model the number of cases of skin cancer as a function of city, Dallas and Minneapolis, and then the age group. And we set as an offset the logarithm of n, the number of people in each city and age category. And then you specify it in the family Poisson, because we are dealing with counting data, and you specify that the link is just the logarithmic link. And here you fit your model, you put everything here in model skin cancer, and you now are to give you a summary of the results. And these are the results you get. And Here it is the residual deviance. Here you are comparing your model with the perfect model, with the saturated model. And if you have repeated data, and you have repeated data here, because for each combination of city and age group, you have several individuals, then this deviance should come from a chi-square distribution with degrees of freedom n minus p. What is n? N is the number of repeated observations you have at every level of the covariates. In this case, we have 6 age groups and we have 2 cities. So that is in total 2 times 6, 12. So we have here 2 cities and 6 age group. Try to visualize that as a table where you have on the rows the cities, and then you have on the columns the age groups. And in each cells, you have a number of individuals. And from that number of individuals, you have a number of skin cancer, right? So you have in total 12 and minus P, and P is the number of parameters in your model. We have here 9 parameters in our model, so you can see that the degrees of freedom is indeed 7. Now, if the model is approximately correct, then these two numbers over here should be more or less similar. The model is correct, this should be chi-square distributed with these degrees of freedom. And this is indeed what you observe when you carry out the deviance test. Here you have the p-value for the deviance test is non-significant. Here you have the p-value for the Pearson chi-square test is non-significant. So this seems to be a good model. If you plot, for instance, the residuals, the deviance residuals, here you have the 0 line, and you can see that the residuals just fluctuate around 0. Here you have the corresponding confidence bands, and indeed the 0 line is included inside these two confidence bands. So in general, no reason to worry here. This model seems to be capturing at least the main features in the data. Now, if you want to, for instance, remember that here you have this categorical variable, which is the different age group. And if you want, for instance, to test now is there is effect of city, or there is effect of age, you can use, for instance, the ANOVA function. And you can pass your model here, and you put I want to do a likelihood ratio test, type 3 sum of squares. So we are going to compare always with the full model. And here you have the p-values for the city, highly significant. There is indeed a difference between these two cities regarding the incidence of skin cancer. And also you see that age is also important, highly significant. We have age does have an impact on the number of cases with skin cancer. And as you can see, if you use the Wald test, you again get the same type of results, highly significant effect of CT, highly significant effect of age. Now, the Wald test, you can do it in 2 different ways. You can do it using the ANOVA function. And in that case, if you pass your model and you put the Wald test type 3 sum of square, you get immediately the effect for the whole variable age range. You can do it also with another function in R, this Wald test over here, but then you pass the coefficients you have in the model. You have the variance covariance matrix of the coefficients, and you said, I want to test the terms 3 to 9. These are the terms associated with the age in the model. And as you can see, then you get exactly the same results you will get if you do it all or everything in one go using the ANOVA function. These are 2 equivalent ways of testing the effect of age using the Wald test. Okay, good. We have our model. We see that we have a highly significant effect of both variables, the CT and also the age, and we see that the model seems to be capturing well all the features in the data, no specific pattern in the deviance residuals, the deviance test, the Pearson chi-square test, nothing there, so the model seems to be doing the job well. Let's now interpret the results. If you look at the coefficient here and you exponentiate the coefficient of CT, then you get this value over here. This is the exponent of the coefficient of CT, and here you have the confidence interval. How should we interpret that? Well, this is Dallas. This is the dummy variable for Dallas. What this coefficient means? Well, what we saw before, compared to Minneapolis, the risk ratio of cancer is 2.23 is 2.23 within the levels of covariance. What that means? Well, essentially means that for each specific age group, the average number of skin cancer is 2 times about 2 times larger in Dallas than in Minneapolis. So for the individuals between 15 and 25, for the individuals larger than older than 85 years old, for each of these age groups, you have that the average number of skin cancer is about 2 times larger in Dallas than in Minneapolis. That is the interpretation of the coefficient. It's a very intuitive interpretation. What about the age? Well, here you have the difference estimates. This is the exponent of the coefficient you got for the age between 15 and 24. What would be the interpretation of that? So now you have to observe here that the reference category was the 85 plus. That's the oldest group, right? So you need to interpret this relative risk now in comparison with the oldest group. So compared to the oldest, the risk ratio of cancer is 0.002 within the levels of the other covariates, or if you want in each city, the average number of skin cancer for the youngest. So what you have here is that if you have, for instance, Dallas, it will be the same for Minneapolis because we don't have interaction between city and age in this model. So it will be the same for both cities. If you compared the youngest one with the oldest one, if you compare the group between 15 and 24 with the group of 85 plus, what you see is the average number of lung cancer in the young group is 0.002, the average number of lung cancer, skin cancer, sorry, the average number of skin cancer in the oldest group. Of course, the incidence is a lot lower in the younger group, as one may expect. So these are the conclusions. It's a very nice model. It has a very intuitive interpretation. In this specific application, everything seems to be working right. So it's a very simple analysis. And what we are going to do here is we are going now to show, we're going to use the model to predict, for instance, here it is. For instance, suppose that you have now, we have predicted the number of individuals with skin cancer now for per 1,000 inhabitants. So here you have predicted number of cases per 1,000 inhabitants. Or the predicted number of cases, for instance, for one inhabitant. What is the probability that one person will have this skin cancer? And here you have the predicted number of cases for the number of cases we actually had in the data set. And here you have, for instance, per 1,000. In the category 85 plus, here you have how many cases you predict in Minneapolis. You will predict about 4 cases in Minneapolis. And now in the same category in Dallas 85 plus. Now in Dallas, the model will predict about 9 cases. And as you can see, is in Dallas larger than in Minneapolis. How much larger? These 2.3 that we saw before. So that is what the model predicts. You will get 2 times more cases in Dallas than in Minneapolis for each age category. And what about comparing 2 different age categories? For instance, here you have the number of cases between 15 years old and 24 years old. This is the predicted number of cases for skin cancer in that category. And here you have the predicted number of cases in the category for 85 plus. And you can see that as the model, as we saw before, the number of cases here is 0.002, approximately the number of cases over here. And that's exactly the same also for Dallas. Much less cases in the younger group than in the older group, as one would expect. And here, this is what the model predicts for the data. So the model predicts, for instance, that in this group between 15 and 24 in Minneapolis, you should have a 1.5 number of skin cancers. The observed data tells you 1. For instance, in the category between 45 and 54 in Minneapolis, the model predicts about 79 cases. We actually observed 71. So the model actually makes very good prediction. For instance, in the category between 75 and 84 in Dallas, the model predicts about 240 cases, 239 cases. The actual number of cases was 226. So the model seems to be working fine. Now, you may ask, well, why do we have so much more cases, why the number of cases in skin cancer cases is why it's much larger in Dallas than in Minneapolis. And if you look at the map in the US, you immediately get an explanation for that. As you can see, Dallas is a lot more to the south than Minneapolis, and we know that the biggest risk factor for skin cancer is actually exposure to sunlight, to this ultraviolet light. So that's the reason why um, you have much more cases in Dallas than in Minneapolis. But it's a nice example in which you have your GLM model, your Poisson, your log linear model, and it really works beautifully here. Okay, now we are going to study a more complicated example, an example in which the model doesn't do the job so nicely, and we need to make some adjustments. And in this case, we have an study. It's a research that tried to analyze the number of publications produced by PhD students that were biochemists as a function of a number of variables. So how many articles a PhD student writes? And we want to explore the relationship between that variable and a number of covariates. Again, it's a counting process. Number of articles, it's a counting process. So the response variable is art, is the number of articles in the last 3 years of the PhD. And we want to model that as a function of, for instance, the gender of the student. Does female publish more or less as an average than males? We want to also take into account the marital status. We call that MAR. Is single people, do they as an average publish more or less than people that are married? The number of children under the age of 6. The prestige of the program that they are following, and mentor, which is the number of articles that the supervisor published in the same period of time. These are the variables we want to consider. And if you are interested, here you have the reference for this case study. Okay, here is our data set. You have the variables, the number of articles published by the student, the gender of the student, the marital status of the student. Then you have the number of children under 5 years. Then you have this, the prestige of the program is some kind of index. And here you have the number of articles that the supervisor published in the same period of time. Let's try to fit the model. And okay, we do the same. You use the GLM function and you're saying, I want to model the number of articles as a function of all these covariates. Is a counting process, number of articles. So the family is Poisson. And I tell R to go here to look for the data. I fit the model and I put it here. And once you do this, you get your fitted object. You ask R to give you a summary of the results, and you get the coefficient table over here. And if you just look at the table, you see that everything except the prestige of the program, the PhD, everything was significant. So if you look at here, well, it seems that women are actually publishing less than men. The coefficient is negative for women. It's highly significant. It seems that single people are publishing less than married people. You hear the p-value, highly significant. And you have here also that children, kind of the number of children, small children, affects in a negative way the number of publications. Everything that seems also to be plausible. A very highly significant p-value. The prestige of the program doesn't have any impact whatsoever. And the number of publications of the mentor, it does have a positive impact. So the larger the number of publications of the supervisor, also the larger the number of publications of the student, and that's highly significant. So these are the conclusions from the model. However, this is just what we have discussed. However, if you look at the residual deviance, you see that it is huge compared with the degrees of freedom. Remember, if the model is correctly specified, these two things should be more or less equal, because if the model is correctly specified, this, and you have repeated observations, then this should be a chi-square with these degrees of freedom. Now, you may be careful here, because we may not have here a cluster data, repeated observation for each value of the predictors, because we have some continuous variables here, or quasi-continuous variables, the number of children over here, the PhD covariate over here. So you need to interpret this in a careful way, but it can always give you an idea. So we may have a problem with this model. Now I'm going to take this opportunity to show you another model checking tool, another diagnostic tool. We have seen already, I introduced that with the logistic regression, and I'm going to introduce now another tool with the Poisson regression. We have seen the residuals, the VN's residuals, we have seen the Pearson residuals, and we have seen that we can use this the VN's test, and we can use this chi-square test. But the problem is that all this is interpretable when you have these repeated observations. So when you have for each level of the covariate repeated observations. It's like, for instance, when you have categorical data that you know for every woman, or like, for instance, in the skin cancer example, when you know that for every city and age category, you have repeated observations. You have several observations between 25 and 30, for instance, in Dallas. In that situation, it's very easy to interpret, or it's easier to interpret these Pearson residuals and the Devian residuals. In that cases, you can apply the Devian test and you can apply the Pearson chi-square test. But if you don't have repeated observations, like for instance, when you have continuous covariates, then these two tests, the Devian test, the Pearson test, are not valid. And also, the interpretation of the residuals become much more difficult. So what we are going to introduce now here is an alternative definition of residuals that can be applied more generally, and that has also an easier interpretation, in my opinion. And these residuals are based on the idea of simulation. So what we are going to do is the following. You are going to simulate now the response variable for each value of the predictor. So you have here the vector with the predictors, and you're going to use the model. So you're going to assume that the model is correct. You're going to use the model, and you're going to start simulating responses for these values of the predictors. For each value of the predictors, you are going to simulate the response. How many times? Well, that is something that needs to be defined. I'm using the default R is using here, and I think that is 250 times. So for each value for the predictors, I'm going to simulate my response. Now, for each value of the predictors, you have now several responses generated with the model. So you're assuming the model is correct. If the model is correct, I can use it to generate the response. So now for each value of the predictor, you have several responses, several values of Y. And now you're going to use these values of Y to construct the empirical cumulative distribution of Y for this specific value of the predictors. If you don't remember what is the cumulative distribution, Google it. The empirical cumulative distribution is an estimator of the cumulative distribution. It's essentially the probability that you will observe an outcome of your variable is smaller than certain value. So essentially, the cumulative distribution evaluated in Y0, let's say, is the probability, is very difficult to, is the probability that your response variable is going to be smaller or equal than Y0. That is the cumulative distribution. And empirical cumulative distribution is an estimator of that. So let's go back. For each value of xi, assuming that your model is correct, so you're going to use your model to generate several responses for each specific value of xi. So now for each xi, you have several y's, and you're going to use that y to construct the empirical cumulative distribution. Right? And what this cumulative distribution gives, well, it gives you the possible values that y can take for that specific value of the predictors and the corresponding probabilities. All this is, of course, assuming that the model is correct. That's it. Now we can define the residuals. The residuals is then the value of the empirical cumulative distribution evaluated on the actual value you observe for xi. So for xi, you observe certain value. Let's call it y observe, y ops, where now you take this cumulative distribution and you evaluate it in the observed value. And that's your residual. Now, so for instance, a residual of 0, what is the meaning of that? That means that all the simulated values were larger than the value you actually observe there. That may be an indication of something is not right with that model. Because what you did is you assume that the model is correct, you generated values of y, but all these values you generated happen to be smaller than the one you actually observe. So the model kind of predict values that are smaller than what you actually observe. That will mean a residual equal to 0. What will mean a residual equal to 0.5? Well, that will mean that half of the simulated values are larger than the observed value. 50% are larger, 50% are smaller. And that would be kind of okay, because that's what you would expect with some random variability there. Now, here comes the important thing, is that if you can show that if the model is correct, then these residuals defined in the way we have done here, if the model is correct, then the residuals we have defined here, they should follow a uniform distribution. So the distribution of the residuals should be flat. And that is so regardless of the model you are using. So you can use this residual for the Poisson model, for the binomial model, for models with random effect. It doesn't matter. If you construct the residuals in this way, then the residuals should follow a uniform distribution if the model is correct. So any departure from the uniform distribution is an indication that your model is not correct. And you can use this type of residuals as well with logistic regression, or also with linear regression. Of course, there is a lot less interested because the residuals in linear regression are very easy to interpret. But when you move away from the linear model and you start working with a Poisson model, or you start working with logistic regression model, the residuals, the classical residuals, the VNs residuals, or the chi-square residuals are a little bit more tricky to interpret, especially if you don't have repeated measurements. So here you have, this is, we are generating here, this is the code in R to generate the residuals. This is something that is implemented in this library over here. And you have here two plots, a QQ plot, and you have these quantile deviations residuals. Now, what is it? Well, the QQ plot is here to assess not normality, is here to assess that the distribution of the residuals is uniform. The same way you can construct a QQ plot for normality, you can construct a QQ plot as well for a uniform distribution. Here you have the Kolmogorov-Smirnov test, which is a test that is evaluating if the distribution of the residual is actually uniform. And as you can see, we get a p-value of 0. So we reject the null. The residuals are not following a uniform distribution. And that's an indication of a misfit. It's an indication that the model is not capturing the main feature in the data. And then here you have the quantile deviations. What is that? Well, here you have the 25% quantile coming from a uniform distribution. Here you have the 50% quantile from a uniform distribution, and here you have the same. And the lines are the ones you get when you use the residuals, are the quantiles you get from the residuals that should be uniform. And you see, obviously, we know already from this test over here that they are not uniform, and you see it also in the quantiles. You see here that this is the quantile you get when you use the residuals, and the horizontal lines is the quantile of a uniform distribution. Here again, you see that there is a problem, and you get this message from our quantile deviations data. This is the red curve. So the model is getting wrong. I mean, the residuals are not following the 50% quantile and 25% quantile of a uniform distribution. So we seem to have a problem with this model. And here you have just a histogram of the residuals. It should be uniform, so it should be kind of a flat line. And as you can see, the residuals are clearly not following a uniform distribution. You have a couple of outliers here. These are values of the response that were not in the envelope of the simulated data. They didn't appear in the simulations. And this is another interesting graph that can help you to assess how good the model is fitting the data. It's called a rootgram. What you have here is you have this dotted line over here. Well, it's not dotted, but you have this line here. This is what the model predicts. So for instance, the model predicts this number of 0 cases, the red ball. And then you have the bar. and the bar is the actual number of zero cases that we observe. And as you can see, the bar goes under zero. You can see here, nothing wrong with that. It's not that the counts are negative, not at all. What that means is that this is what the model predicts. And if you push the bar up, you will see that the bar will come over here, right? If you push it up so that the bottom coincides with the axis, then what you see is that the model is actually under predicting the number of zeros. So the model predicts a number of zeros that is smaller than the actual one. That is given nicely in the graph by pushing the bar down, so you get this part of the bar under the zero axis. That just means that the model is underestimating the number of zeros. The model should give more zeros. The data have more zeros than what the model predict. Then you have some bars that are just hanging in the air, like in these cases, and that's just the opposite case. So here the model is predicting more values than what actually we observe in the data. We have it here, for instance, with 2, this is 1, and here with 2. This is what the model is predicting, and actually is predicting too many 2s. There should be less. So if you push the value, the bar down so that it touches the axis, then you will see that the model is predicting too many 2s. So clearly, whether you look at the previous graph over here, or the previous graph over here, or the rootogram over here, we see that the model is misfitting. We are actually missing important features of the data here. Now, when you have this type of situations, well, here you have the test of uniformity. So here we are testing if the residuals follow a uniform distribution using the Kolmogorov-Smirnov test. Look at this, 10 to the power minus 9. So clearly the residuals are not uniform. And that means we have a kind of misspecification in the model. Now, when you have this type of misspecifications in Poisson regression, one thing that you need to always think of is dispersion, because the Poisson distribution makes this very strong assumption. It assumes, well, it predicts, it states that the mean and the variance should be equal. Now, in reality, that doesn't happen frequently. And what happens frequently is that you have what is called overdispersion. The variability in the data is larger than the mean. The variability in the data is larger than what the model predicts. And then this library, this Darman library, has also a very nice test for dispersion. And it will help you to detect both overdispersion and underdispersion. And what it does is the following. As I said, what you do is you simulate data using the model. Right? For each value of the covariates, you simulate several responses Y for each value of the predictors. Now, what you do is the following. For each generated data set, you calculate the variance of the Pearson residuals. And what this function does is the function compares the variance of the Pearson residuals you obtain from the simulated data with the variance of the Pearson residuals you actually observe. And by doing that, you can get an idea if what the model predicts is the variance that you predict with the model is smaller than the real variance or is larger than the real variance. When you do this, in this case here, you get this histogram over here. This is the variance of the Pearson residuals predicted by the model. So if the model is correct, you generate these responses for each value of the covariates using the model. If that is correct, then the variance of the Pearson residuals should be in this range with these specific probabilities. This is the histogram. And here you have actually the observed variance. It's way larger than the one you may expect if the model was correct. So you may have here a problem of overdispersion. The observed variance seems to be way larger than what you could expect under the model. So the models do not fit the data well. There seems to be a problem for dispersion. Even if you calculate just the unadjusted variance and mean, just calculate the variance of the y's and the mean of the y, you will see that the variance is indeed larger than the mean, and that is clearly in contradiction with what the Poisson distribution states. Okay, what can we do? So we have seen here two examples. In one example, the example of the skin cancer data, everything was nice. The models seems to be doing fine, but now here we see that we have a problem. We may have a problem of overdispersion, or maybe another problems as well, but overdispersion is clear. We seems to have a problem of overdispersion here. How we can solve this problem? We are going to see three solutions. We are going to make use of the sandwich estimator of the covariance to get uh, robust inferences. We are going to use something called pseudo or quasi maximum likelihood estimation. And we are going to introduce two alternative models, the negative binomial model and the zero inflated Poisson model. These are the solutions we are going to propose here to handle over dispersion. Some of these, the first two, the sandwich estimator and the quasi likelihood, you could also use them not only for over dispersion, but when you suspect other types of problems with your model. But let's take first a short break, and then we come back to start analyzing these solutions. Okay, let us start seeing the possible solutions to this problem. And the first one we are going to see is the use of the sandwich estimator. Now, again, I refer you to the first lectures about statistical inference. And that's why we took some time there, because it's fundamental to be able to uh, analyze and go through the different models of the GLM family. The sandwich estimator. Now, typically, um, when you analyze data and you assume a model, you base yourself on the idea, on the assumption that the model is correctly specified. So, or at least that the model is able to capture all the main features in the data. But strictly speaking, we assume that the model is correctly specified. Now, suppose that you got it wrong. Suppose that the data generating mechanism, the data generating procedure, we call it DGP here, is not what you assume. So you assume a model, a density that has certain covariance x and is described with certain number of parameters theta. That's what you assume. But suppose that you got it completely wrong. So actually, the data generating mechanism follows a completely different model or distribution with different covariates, and of course is governed by different parameters. So you got your model completely wrong. What happened then? Well, we saw it in the first part of the course. The maximum likelihood estimator then tries to give you the best he can. And what it is? Well, the maximum likelihood estimator is going to converge to the value of the parameters theta. We will call that value theta aster. So it's going to converge to the value of theta. We call it theta aster over here. That makes your model closest to the true model. So you are going to get it wrong. Of course, you are going to get it wrong. You are dealing with the wrong model. But the maximum likelihood procedure is going to give you the values of the parameters that make your model as correct as it can be. And what I mean by that is the value of the parameters that make your model as close as possible to the true. And when I say as close as possible, what do I mean? Well, close in the Kulbert-Leiber sense, in the Kulbert-Leiber information criterion sense. It's called the clique over here. And the clique is just given by this expression. It's just an expected value of the logarithm of the true divided by your model. And you're taking the expected value with respect to the true model, of course. And this you can show mathematically that it's not strictly a distance, but it's like a distance. This is somehow telling you how far is your model. In general, if you have two densities P and G, it's telling you how far P is from G. In this case, it's telling you how far is your model P from the true data generating mechanism G. Now, the maximum likelihood procedure converges to the value theta aster that minimizes that distance. That's what maximum likelihood does, and is to a certain degree the best you can do. The best you can do is try to find the parameters that put you as close as possible as you can, as close as possible to the true mechanism. Another way to reformulate this is that the maximum likelihood will converge to the value that solve this equation. So you take your score equations using your ROM model, because remember, the true is not P, is G. You take your score equations using the ROM model, and you calculate now, this is a function of Y, obviously, and you calculate now the expected value, but now with respect to the true of this equation. The value of the parameters that solve these equations, this is theta aster over here. This is the value that minimizes the distance between your model and the true. So that's what the maximum likelihood will do if you get your model wrong. But now you can show that the maximum likelihood estimator then will converge, as we said before, to this value that minimizes the Kullbaum-Leibler distance, and it's going to be asymptotically normal. But now, of course, it's going to be asymptotically normal, which means the value theta aster, the one that minimizes the clique, and then certain variance covariance matrix, and this variance covariance matrix is given here, is given over here. So that's why we call it the sandwich estimator, because here you have like the butter, and here you have like the bread. And this matrix, well, is called obviously the sandwich variance covariance matrix. Now, here is the detail. For log linear models, if the mean is correctly specified, so if you manage to specify the mean structure correctly, the systematic part correctly. Remember, in GLM, you have the systematic part and the distribution part. Well, if you manage to specify the systematic part correct, so if there is actually a value beta 0 for which the actual mean of this counting process is given like this, so if you manage to specify the mean correctly, then the theta aster will be equal to the true value of beta 0. So the maximum likelihood will converge to the true value of the parameters. But you need to make sure you specify the mean correct. And then, even though the distribution part may be incorrect, that's for instance what happens if you have overdispersion, because if you have overdispersion, the distribution of the data cannot be Poisson, because in Poisson, the mean and the variance, they have to be equal. But that's okay. If you specify the mean correctly, then you can make inference for beta 0, even if the distribution part is wrong. Why is this general result we got here? You can use the sandwich estimator and you can get correct inferences. Typically, you will get correct inference for theta aster. But if you specify them incorrectly, then actually you can get theta aster is equal to beta 0. You can get correct inferences for beta 0. But again, at least the mean needs to be correctly specified. And how you can do that in R? Well, for instance, if you're dealing with the Poisson distribution, you fit it your model, and now you can use, it's in the library LM test, you can use this command here, coef test, and you pass your model, but then you say variance covariance matrix sandwich. You don't want to deal now with the normal variance covariance matrix because you know your model is not correctly specified. You know that we have this overdispersion problem. But then if you specify the mean correctly, so we are still assuming that this part of the model over here is correctly specified. So the mean, the logarithm of the mean is given by this model over here that contains, well, the intercept, gender, marital status, number of kids, PhD, prestige of the PhD program, the number of papers of the mentor. You need to assume that that part is right. But if that part is right, and the problem is that you have overdispersion, then you can still get correct inferences for these covariates just by using the sandwich estimator. And it does make a difference because, for instance, if you look at marital status in the Poisson model, you got a highly significant p-value over here. However, when you use the sandwich estimator, it is not significant anymore. It's about 0.6, 0.06. So it does make a difference. But now the results we are getting here are going to be valid even if you have overdispersion or if you have underdispersion. It doesn't matter. The only thing you need is that you need to get the mean right. But if you get the mean right, then you can use this sandwich estimator to make correct inferences about the parameters of the covariance, the FET of the covariance. Now, for instance, you may use the Wald test because if you look at here, you see that there are two variables that are not significant. One of them is the prestige of the program over here, PhD. The other variable is marital status. So I'm going to compare now two models, a full model that contains all the covariates and then another model, a reduced model that doesn't contain these two because these are not significant. And we are going to make that comparison between these two models using the Wald test. But I'm going to use two versions of the Wald test. I'm going to use a version that uses the sandwich estimator. And I'm going to use a version that simply is using the Poisson model. And as you can see, again, if you use the sandwich estimator, here you are comparing a full model that has everything with a model that doesn't have a PhD and MET, these two that were not significant. And if you use the sandwich estimator, you get a non-significant p-value, so you can stay with the model over here, the most parsimonious model. However, if you use just the Poisson regression model, then you get a highly significant p-value. And then you will have to stay with this model. However, this test is problematic because we saw the residuals, we analyzed the data. This model, the Poisson model, is not appropriate here. We have at least overdispersion. We saw that we have overdispersion. We may have other problems as well, but at least we have overdispersion. So this is the correct analysis in this case, of course, assuming that you got the mean right. If you also got the mean wrong, then, well, there is very little we can do. The whole model is wrong. But if you get the mean right, you can still make correct inferences for the mean parameters, even if the distribution is wrong. So you need to get the systematic part correct. That's the sandwich estimator. Another procedure that we can use is the so-called quasi-likelihood. Now, what is that? Likelihood-based inference, like everything we saw in the first two lectures, they are based on the assumption that the complete distribution is correctly specified, right? Because the likelihood is just the probability of the data, so you need to get the probabilities right. So the likelihood machinery works based on the assumption that the whole distribution of the data, the ones you use to construct the model, is correctly specified. Now you can follow a little bit of a less parametric path here. You can assume that some parts, some aspects of the distribution are correctly specified, while others, well, are left completely unspecified, or they may be misspecified. So you don't want to demand that the whole distribution is correct. You are going to demand that some aspects of the distribution have been correctly specified, a little bit like we did with the sandwich estimator, and other aspects of the distributions are not going to be correctly specified. So, by the way, when you use the sandwich estimator, if you compare here, let's go back because I think it's important, you see that the point estimates are exactly the same. And of course, they are exactly the same because you're assuming that the mean structure is correctly specified. So you have these score equations that are going to be exactly the same. The only thing you're doing is you are just correcting the standard errors using the sandwich estimator. Now, quasi-likely. Well, when you use these methods that do not necessarily assume that the whole distribution is right, but just some aspects of the distribution are right, you call these methods quasi-likelihood method or estimating equations method. We are going to see more about that shortly. So essentially what you do is that you specify the mean and the variance separately. Typically, if you have a Poisson distribution, then when you specify the mean, you have the variance, right? Because there is a link between the mean and the variance. And that's frequently the case in the GLMM family, not for the normal data. For normal data, you specify the mean and the variance is allowed to vary still freely. They are two independent parameters. But typically, in most members of the GLM family, the variance and the mean are linked. If you specify the mean of a binary distribution, a Bernoulli distribution, a binomial distribution, a Bernoulli distribution, you immediately specify the variance. Because if you specify the mean is n times pi for the binomial data, but then the variance is n times pi is 1 minus pi. So once you have the mean, you have the variance. That comes from the distribution itself. Like in Poisson, you have the mean, then you have the variance. They are the same. That's what Poisson distribution implies. Now, in quasi-likelihood, you're going to specify these two things separately. You are going to specify the mean, and you're going to specify the variance. Of course, these means and this variance may not correspond to any proper distribution. Because, for instance, you can, in the Poisson distribution, you can try to model over dispersion using the so-called scale model. So you specify the variance of y not as lambda, but as psi times lambda. So now you specify the mean, and you specify this variance function. And you put this psi over here because you know you may have over or under dispersion. Now, this doesn't correspond anymore to a Poisson distribution, because for the Poisson distribution, this psi over here has to be equal to 1. Because for a Poisson distribution, the mean and the variance are equal. So you are not dealing now with a proper probabilistic distribution maybe, but it doesn't matter. Doesn't matter. That's the idea of quasi-likelihood. You separate the mean from the variance. You specify the mean, and then you specify the variance in an independent way. Now, the mean structure, which is given here by the response function, again, must be correctly specified if you want to get consistent estimators for beta. So to get correct inference for beta, you need to make sure that the mean structure is correctly specified. Now, the variance function over here must be correctly specified to get correct standard errors for beta. So if you want to get not only correct estimators, but correct standard errors, then the variance needs to be correctly specified as well. Now, essentially what you're going to do is you are going to find something called a quasi-maximum likelihood estimator for beta, and then you are going to use this quasi-maximum likelihood estimator to estimate the psi you have used here. But let's see this in more detail. So for instance, here you have the publication data, and now the way you fit this quasi-likelihood model, the only thing you do is that you just specify the GLM family and then family quasi-Poisson. And we are going to see in the next lecture all these more in a theoretical methodological framework that will allow you to understand a little bit better what is going on. But I mentioned it already here, and then in the next lecture, we are going to see this a little bit more formally. And here you get exactly the same point estimates, because essentially it's going to be the same score function as when you use Poisson, but the standard, you see now, for instance, this over dispersion parameter that in the Poisson model, this is psi. In the Poisson model, it should be equal to 1. And when you use the quasi-likelihood, you get an estimate that is clearly larger than 1, is 1.83 more or less. So you really see that you have over dispersion here. So the variance is about 83% larger than the mean, because remember that as we put here, we are modeling now the variance as a psi times the mean. This is not anymore equal to the mean, but psi times the mean. And you see that psi is about 1.83. So the variance is 83% larger than the mean. We do have over dispersion here. And you can see that the standard error are now larger. How much larger? They are about 35% larger. Essentially, what you are doing is you are multiplying the standard error you get from the Poisson distribution by the root square of this psi here. And you can show that that is actually the case theoretically. But we are going to talk more about that, the methodological details, in the next lecture. And another important part is that you see that R is not giving you the AIC anymore. And it's not giving you the AIC essentially because you are not having a likelihood here. This variance function that we specify over here doesn't correspond to any correct likelihood, because for the Poisson likelihood, the variance should be equal to the mean, and we are not doing that here. That's why you don't get a likelihood. You specify now an AIC. You specify the mean, and then you specify a variance. And you specify the mean in this way, and you specify the variance in this way. But this variant mean pair that we are specifying here, this does not correspond to proper likelihood. Because for the Poisson, the psi should be equal to 1. This should be equal to 1. And that's the reason why R is not giving us an AIC, because the AIC is obviously based on the likelihood. So we do not get an AIC here. It doesn't make any sense here to talk about likelihood inference like an AIC. We do not have a likelihood here. Okay, so let's compare the results we get when you use the classical Poisson distribution or when you use this quasi-likelihood approach. And as you can see, again, you get different results. Because when you use this quasi-likelihood approach, for instance, marital status is again non-significant, it's 0.06. When you use the Poisson model, you do get a highly significant result. So it makes a difference this which approach you're using here. Of course, we know that this is not correct. We have a strong evidence that we have over dispersion. This psi value, if you remember when we fitted the model over here, the psi value was about 1.83. So the variance is actually larger than the mean. Okay, that is the quasi-likelihood. So we have seen until now two different approaches. One approach is the sandwich estimator. What you do with the sandwich estimator? With the sandwich estimator, what you do is, well, we know that if we got the model wrong, then the maximum likelihood approach will converge to the value of the parameters that make my model closest to the true. Closest in which way? Kullbaum-Leibler. Fine. Now, if you get the mean structure correct, if you get the systematic part of the model correct, then the maximum likelihood will converge to the true values of the betas. And then it's okay, because then you know that the maximum likelihood, even when the model is misspecified, the maximum likelihood is going to be asymptotically normal. And now it's going to be asymptotically normal with mean equal to the true value of the betas, because we specified the systematic part correctly, and variance covariance matrix that is given by the sandwich estimator. And now you just need to use the sandwich estimator, and you can make the WAL test to, for instance, evaluate if certain variable has an impact on the response or not. And the model doesn't need to be correctly specified. The only thing you need to get right is the mean. That's the sandwich estimator. The quasi-likelihood is a little bit similar, but in the quasi-likelihood, you do specify the mean and the variance. In the sandwich estimator, we didn't worry about it. The mean is correct, fine. You know, we just get our inference. Now, in the quasi-likelihood, you specified the mean and the variance. Now, you only need the mean to be right. You only need the mean structure to be right. The variance is called a working variance. Now, if you get it right, better, but you don't need to. And for instance, if you have over-dispersed data, you know that the Poisson implies that the mean is equal to the variance, but that's not correct. So you add this psi, this multiplicative parameter there, to guarantee that the variance is not equal to the mean. It's not equal to lambda, it's equal to psi lambda. It may be larger, it may be smaller. And then with these two specifications, you can apply quasi-likelihood and you can get correct inference as well. Now, as you can see, we got this side that was much larger than one. We have clear evidence that we have over dispersion here, and then the standard errors were corrected. And if you got the mean right, this procedure will also give you right inferences. And now, the other possible solution is to just change the model. Now we are going to use, if you look at sandwich estimator or you use to quasi-likelihood, these are not likelihood methods in the sense that, well, the sandwich estimator is a likelihood method because you have a model, but you don't need the model to be right. You just need some part of the model, the mean structure, to be right, and then you just use the sandwich estimator. And with quasi-likely, kind of the same. Now, we are going to do we are going to use another model, and we are going to assume that this alternative model, of course, is correct. And this model is called the negative binomial model. And it's a model that you typically use when you have over-dispersed data. Now, the negative binomial model is based on the negative binomial distribution. And what is the negative binomial distribution? Well, there are different versions of the distribution I'm going to give you here too. The first version is you count the number of trials at which you get a number of successes. Let's call white successes. So the number of trials at which white successes happen. So suppose that you are tossing a coin and is the number of trials at which I will get 10 heads, right? And the negative binomial distribution just give you the probability that you will have to do n trials before you get y successes, right? So what is the probability if I want to get 10 successes? What is the probability that we'll need to do 10 trials? Of course, n needs to be larger than y. And the probability of having success in one trial is given by pi. So if I'm choosing a coin, what is the probability that I need to do 10 trials to get 10 successes? What is the probability that I have to choose the coin 50 times to get 10 successes? So it's the number of times you have to try until you get 10 successes. That's a version of the negative binomial distribution. But that's not the one we are going to use. There is a second version, and that is counts the number of failures before you get y successes. So let's say you need to fail 10 times before you get, what is the probabilities that I will fail 10 times before I get 2 successes? What is the probability that I will fail 60 times before I get 3 successes? So this is just the probability function for the negative binomial is given over here. It's just the probability function. And x is the number of failures, and pi is the probability that you will get 1 success in 1 trial, and y is the probability of successes that you have fixed. So, and you want to calculate what is the number of failures I need before I get pi successes. For instance, see what is the probability that I will get immediately the y successes with no failure. What is the probability that I will fail 1 time before I get y successes, and so forth. Now we are going to work with this version of the negative binomial distribution. There are several versions, but we are going to work with this one, which is sometimes called the Pascal distribution. It's the same. Now, suppose that you have a variable x that follows a beta binomial distribution. Here you have y, the number of successes. Here you have the probability of a success in 1 trial. You can show that the mean of x, the average is the average number of failures before you get y successes is given by this expression over here. That's the mean of a negative binomial random variable, and this is the variance of a negative binomial random variable. It's given over here. Now, if you work a little bit of algebra here, you realize that for the negative binomial, the mean and the variance, so the variance is actually a quadratic function of the mean. If you call this mu over here, then you can write the variance in this way: mu plus a constant times mu squared. So the model assumes that you have a quadratic relationship between the mean and the variance. Now, the quasi-likelihood models assumes a linear relationship, because if you have a quasi-likelihood model and you use this expression for the working variance, then you are assuming that there is a linear relationship between the mean and the variance. If you use the negative binomial model based on the negative binomial distribution, then you assume that the means and the variance are related in a quadratic way. So the variance is a quadratic function of the mean. Okay. Now let's introduce the negative binomial model. Suppose that you have here the classical Poisson model. So you have a random variable y that follows a Poisson distribution with mean lambda. And you're going to assume now that lambda, typically in the Poisson model, you assume that lambda is equal to this part over here, the exponent of the linear predictor. Now we are going to assume something different. Lambda is equal to, indeed, the exponent of the linear predictor times another random variable here that we call lambda aster. And this random variable follows a gamma distribution, a gamma with parameters theta and theta. So it's like a modification of the Poisson model. It's not like the pure classical GLM log linear model, but you introduce this multiplicative factor in the mean. Now, notice that if this lambda aster comes from a gamma distribution with parameters theta and theta, then this lambda aster has means 1 and has variant 1 over theta. This is just properties of the gamma distribution. Go on Wikipedia and look for the gamma distribution, and you will see. Now, if you have this situation, so if you have a random variable that follows a Poisson with mean lambda, but now the lambda is not modeled just as the exponent of the linear predictor, but you have also this multiplicative new gamma random variable here. What would be the average of y, the marginal average of y? When you can show that the average of y will be, well, mu, which is essentially like in the Poisson, the exponent of the linear predictor. And what would be the variance? Well, you can show that marginally the variance of y now is going to be just a quadratic function of the mean. So if you made this adaptation to your model, then marginally the mean of y is mu and the variance of y is mu times a constant mu squared. Now, you can show further that if you have gamma following this, if you have lambda aster following this gamma distribution over here, then this lambda is going to have also a gamma distribution with parameters theta and the theta exponent of the linear predictor. You can show that. That if lambda aster is a gamma with parameter theta theta, then lambda will follow this distribution. Fine. What would be now the distribution of y, the marginal distribution of y? Because conditional on lambda aster, then y is a Poisson, right? But marginally. If you integrate out this lambda aster, what you get? Well, let's do it. So if you want to take into account now the marginal distribution of y, you need to integrate the Poisson with respect to the probability distribution of gamma, of lambda, because lambda is a random variable now. So essentially what you're assuming now is that the mean of the Poisson is not a constant. The mean of the Poisson is a random variable itself. Lambda is not a constant that you model using the exponent of the linear predictor. Lambda itself is a random variable that you model using a gamma distribution with parameter theta, and theta the exponent of the linear predictors. And that's the main difference, that in the classical Poisson model, the log linear model, you assume that lambda is a constant and you model it as a function of the predictor. It's not constant in the sense that it depends on the predictor, but it's not a random variable itself. It depends on the predictors. But now in the negative binomial model, you assume that the lambda is itself a random variable with a distribution gamma and parameters that depend on the linear predictor. Now, marginally, what is the distribution of your counts? What is the distribution of y? Well, you need to integrate out the random lambda over here, just using the gamma distribution you get over here. And when you do this, when you calculate this integral, that will be the marginal distribution of your y. And here it is. This is the marginal distribution of y. And this is just a negative binomial distribution. So essentially, you don't need to make all these derivations and assume that, you model the mean of a Poisson as a gamma. You don't need to do that. You can start already here and you say, I'm going to consider this model. So I know that my y is not Poisson because the mean and the variance are not equal. But I can model using the negative binomial because I know that for the negative binomial, the mean and the variance are not equal. For the negative binomial, the variance is a quadratic function of the mean. So you can start directly with the model without having to make any reference to Poisson with a random lambda that follows a gamma distribution. You don't need to do that, but it's nice to see it. So you have this equation here, which is the negative binomial, and you know that this can be interpreted as emanating from a Poisson model, for which now the mean is not a constant, the mean is a random variable that comes from a gamma distribution that has parameters that depend on the linear predictor in this way. And under that assumption, you get the negative binomial model, but you don't need to do that. You can start directly with the negative binomial. So this is called the negative binomial model. And you can fit this model in R, is called GLM-NB, so GLM negative binomial. And that's it. For the rest, you just pass your model like you will do classically in the Poisson model. And then you just can fit your model, put your model in this object, and then you calculate a summary. And here you have the values. Now, as you can see here, you have the estimate of theta. Remember that this theta is important in your model. This theta is what gives you the variance of your response now as a function of the mean. So R will give you that theta over here is 2.26. And here you have again, for instance, for marital status, no significant, is 0.07. Again, remember the Poisson regression, which we know is wrong because we have over-dispersion, was giving you a highly significant p-value for marital status. And if you compare the AIC, wait a minute, do we have an AIC here? Yes, we do have an AIC here. Why? Because now we have a completely specified likelihood. We are assuming a beta binomial distribution for y. So now we are given a completely specified likelihood. And if you compare it, the AIC of the negative binomial with the AIC of the Poisson, you see clearly that the AIC of the negative binomial is better. So this is a better model than the Poisson model. We are not surprised because the Poisson model, we knew that was unable to account for this extra variability, and the beta binomial model can account for that because now the variance is a quadratic function of the mean. So let's put everything together we have done until here. First, notice that the negative binomial and the Poisson model, they do not give exactly the same estimates. They don't. Why? Well, because you have a different model, a different distribution, a different likelihood, a different score function. These things are different. They don't give you the same estimate. The sandwich estimator, of course it does, and the quasi-likelihood too. But the negative binomial doesn't give you exactly the same point estimates, even though they are not very different from the ones you get from the Poisson model. Now, if you look at the standard errors, and this is now what matters, because when you are carrying out tests, of course, you need to use your standard errors. When you look at the standard error, you see that the approaches we use for over-dispersion, so the sandwich estimator, the quasi-likelihood, and the negative binomial, these three over here, these three procedures over here, they give more or less similar standard errors. Not identical, but similar. Now, you see clearly that the ordinary Poisson model underestimates the standard error. These are the ones given over here. They are typically substantially smaller than the one we get by these procedures. And that is just because the Poisson model is misspecified. We have extra variability that the Poisson model cannot explain. Now, as I told you, the quasi-likelihood approach and the negative binomial approach, they made different predictions for the variance. The quasi-likelihood assumes that you have a kind of linear function between the mean and the variance. It doesn't have to be correct, but the model assumes that. But if that is not true, it's okay. The quasi-likelihood still will give you correct inferences because the variance you use is a working variance. But of course, you need to get the mean right. But this is what the model assumes, that you have this linear relationship between the mean and the variance. Whereas the negative binomial assumes that you have a quadratic relationship between the mean and the variance. So you can use that to try to see which of these assumptions is more likely. Do we really have like a linear relationship here between the mean and the variance, or is it more like quadratic? Well, you can check that. So here you have the code to do that. So what you essentially do, well, look at the code, but you just make, like, quantiles. You make breaks, you create categories for the predicted values of the models, and then within that categories you calculate the mean and the variance. You create like intervals, and then you see you plot the mean against the variance. And as you can see, this is what the quasi-likelihood predicts, is some kind of linear relationship, and this is what the negative binomial predicts. Now, the negative binomial, the quadratic relationship, seems to be more plausible here. So you may get better results with the negative binomial, even though the quasi-likelihood, again, is not wrong. But in the quasi-likelihood, you kind of propose a variance function. It may be wrong. In this case, we propose a linear one. If it is wrong, no problem. You still will get valid conclusions for the mean structure, assuming that the mean is right. But of course, the better you get the variance function, the more precise your results will be. And it's clear that here the quasi-likelihood is getting the variance functions wrong. It doesn't seem to be linear, it seems to be more like quadratic. So if I look at this graph, it will support more the use of the negative binomial than the quasi-likelihood. And here you have now the graph, the root graph that we plotted before, now for the negative binomial model. It looks pretty good to me. I mean, you have almost all the bars are on the correct place. There are some little underestimation here and there for some values, but it looks pretty well. So the negative binomial seems to be doing a good job. And if you look now at the residuals in the way we define it, look at here. This is the Kolmogorov-Smirnov test comparing the residuals with the uniform distribution. That looks pretty nice to me. Here you have now this test for the quantiles. No problems are detected. It looks pretty fine to me. So the negative binomial model seems to be doing a good job. And now we are going to discuss the last possibility, is the so-called the zero inflated Poisson models. Now, what is that? Another problem. You can have several problems when you work with the Poisson model. One of the model is just over dispersion or under dispersion. It's basically that the variability predicted by the model is too small or too large. Typically, it's too small, so the data have more variability than what the model predict. But another problem that appears frequently when you are dealing with Poisson regression is the so-called zero inflated Poisson models. I mean, this is the solution. The problem is that you get this zero inflation. Now, What is that? Well, you have too many zeros compared to what the Poisson model will predict. So sometimes when you're dealing with counting data, you see that the amount of zeros you actually observe in the data are too many. The Poisson distribution predicts less zero. For instance, in this case study that we were analyzing, the number of published articles by PhD students of biochemistry, 30% of the scientists in the sample didn't publish any article in the last 3 years. Now that's too much. The Poisson model predicts that they should be around 21%. So this is another problem you may have when you're dealing with Poisson regression, an excess of zeros. So the Poisson predicts that you should have about 21% of the sample that didn't publish, but in reality you have 30%. And how can you deal with this? Well, a way to deal with this is to change the model, to use what we call a zero-inflated Poisson model. What is that? Well, you assume that the data actually do not come from a Poisson distribution, but come from a mixture of two distributions, or a mixture of two populations. One where the counts are always zero, and another one where the counts follow Poisson distribution. So when you use this model, you assume that your population is divided in two groups. One group has response zero, just zero, and the other part of the population has a response that follows a Poisson model. So your response Y is a mixture between these two distributions. It's a mixture between these two subgroups. Okay, let's put this a little bit more formally. So the zero inflated density is a mixture between two densities, one that has whole mass at zero. We denote that by I0Y. So this is just the part of the population that just has always Y equal to zero. And then the other part that just follows a count distribution typically is a Poisson distribution. And this thing can depend on covariates, parameters, just like we have seen before. Now, the probability of observing a zero count is now inflated because the Poisson distribution predicts some amount of zeros, but we have added this part, which is always the group in the population that always have Y equal to zero. Now, what is the probability that one individual will be in this group? Well, you model this probability, you call it pi, you put a model on it. You model what probability that an individual will belong to the group that always has response equal to zero, and that probability you can model using, for instance, logistic regression. So you can model that probability using covariates and using parameters, etc. Now, what is the zero inflated model? Well, the probability, the distribution of Y now is a mixture between two distributions. And what is the probability that Y takes certain value? Well, it depends where the individual is. It's a mixture between this distribution that is completely concentrated on zero and this distribution here that follows a Poisson distribution. It's a mixture distribution. And essentially, this is the probability that the individual will be in the group that always a response equal to zero. And then, of course, 1 minus that is the probability that the individual will be in the group that follows a Poisson distribution. You have actually here like two models. You establish a model for the Poisson distribution over here, but you also establish a model for the probability that an individual will belong to the Poisson category or will belong to the zero category. And you can model that probability using just GLM. For instance, you can use logistic regression. It's a probability, you can model it using logistic regression. And the regression equation of the mean, now you calculate the mean of a variable that has such a distribution as here, what would be the mean of Y now? The mean of Y will follow, this is the mean of Y. It will not be the exponent of the linear predictor, but 1 minus pi, the exponent of the linear predictor. And remember that this pi is also a model. Now, you can use the same covariates to model the pi and to model the Poisson. You can do that. You can use the same covariates for these two models, but you don't have to. In principle, you could have certain covariates to model the probability and different covariates to model the Poisson process, but they could be the same. Nobody says that they have to be different. And in the simplest case, you just model this probability that the individual will belong to the zero group just with an intercept. You don't use any covariance, so you use z equal to 1. And that is also a possibility. Now, you can fit this type of models in R. Here you have one of the implementations you can use to fit this zero inflated Poisson models in R is in the package PSCL. And so let's do it for our data set, this data about the number of publications. So here is the function zero inflated Poisson. You write down here your model as we did before. The number of articles, a function of gender, marital status, number of kids, prestige of the program, and number of articles of the tutor. And then you put this slash over here, and now you are going to start to specify the model for the probability of being in the zero category. And as you can see, we are only using here an intercept. So we are not using any covariate for modeling that probability. And here are the results you get. So this is the estimate for the zero inflation model coefficients for the binomial with the logistic link. So here we are modeling the probability. This is the logistic regression model that we are using to model the probability that an individual will belong to the zero category. We only put an intercept. So here you have the value for that intercept, and it's highly significant. And then here you have just the estimate for the Poisson part, for the coefficients of the Poisson process. Now, this model predicts that you should have 0.28.8. So that's 28.8% of the observation should be zero. And actually, the observed number of zeros was 30%. Well, it's better than the Poisson, because you remember the Poisson model predicted that you should have 21% of the observations with zero, and the observed value is 30. Well, this model improved on that, because if you look at here, now this model predicts that 29% of the observation should be zero, and in reality, you got 30% of the observations equal to zero. So we do get an improvement here. Now, you can also fit this model, but considering now just predictors for the probability of being in the category zero. And you could also use a zero inflated model with a negative binomial distribution. So instead of using a Poisson distribution for the counting process, you use a negative binomial. You can do that as well. It's exactly the same idea, but instead of using a Poisson for the counting process, you use now a negative binomial. So you have a number of individuals that have always zero and a number of individuals that follow a negative binomial distribution. It's the same type of model. And again, you can consider now that you can model the probability of being in the category zero using the same covariance you use for the Poisson model. You can do that. Or you can use different covariance. But in this case, we're using the same one. And well, we fitted the two models, one for the zero inflated Poisson, one for the zero inflated negative binomial. And these are the results we got for the zero inflated Poisson. As you can see, for the logistic model, all the coefficients were not significant. The only one that seems to be highly significant is the number of papers that the tutor published. And this is negative. And that means that if the number of if the tutor publish a lot of papers, then the probability that the student will not publish, that he will be in the category zero, that probability decreases. The more papers the tutor publish, the less probability is that the student will not publish any paper. And that is obviously rather logical. That's what we could expect. And if we look now at the Poisson model, so here is the logistic model, modeling the probability that the individual will be in the category zero, and here we have now the Poisson model. Then you see that, well, women, again, seems to publish less than men. It's highly significant. Marital status, look at this now. In the Poisson model was highly significant. Yeah, marital status is absolutely relevant. The number of children, small children, has a negative impact on the number of publications. And of course, the number of papers the mentor published, this has a positive impact. Again, the more papers the tutor publish, the larger the number of papers the student will publish, if he is in the Poisson part of the population. And it's more likely, the more papers the tutor publish, the more likely it is that the student will not be in the zero part of the population. And if you look at now at the predicted probability, this model predicts about 29.8% of the data should be zero, and the actual observed percentage was 30. So this is, if you use this zero inflated using covariates for the probability, then you even get a better results. Because now this model, when you use the covariates, essentially mentor here, which is the one significant, well, you predict that 29%, 29.8, about 30% will be about 30% will be should be zero, and in reality you got 30%. Now here are all the models we use. So this is just the Poisson model, that we know is wrong. This is the negative binomial model. This is the zero inflated Poisson model, and this is the zero inflated Poisson model, but this is only with one intercept, and this is the zero inflated Poisson model with using covariates over here. The zero inflated negative binomial model really didn't add anything. It was almost the same as for the zero inflated Poisson model with covariates. And if you use the AIC, then you see that the clear winner here is the negative binomial model. Is the one with the smallest AIC. And actually, when we look at the negative binomial model for first time, when we fitted it, you saw that the negative binomial model was already doing a good job. Look at this graph. The negative binomial model seems to be, look at this graph, the residuals, the negative binomial model seems to be doing a good job. And this is confirmed here. We fit all these other models, and still the negative binomial model was the best model, the model with the best AIC. So from this list, the negative binomial is the best. And when you look at the predicted number of zeros, the negative binomial model actually nails it. So you get about, predict that 30%, 30.3% of the data should be zero, and the actual observed was 30%. 30% of the data had y equal to zero. The model predicts 30.3. So the negative binomial model is our best choice here. Now, we had a number of questions. Let me well, we got a question of why we are comparing the age groups within city. Well, if you go back to the model, we don't have any interaction. We didn't consider interaction between city and age. Now, it's a choice in the model, trying to keep the model parsimonious. And when we applied all these chi-square tests and the variance tests, and we look at the residuals, we really have no evidence to doubt that model. So it's a simpler model than if you consider the interaction that seems to fit the data correctly. So that seems to be okay. And the zero model has marital status significant. Which zero model has marital status significant? I mean, if you look at here, this was highly not significant. And this is when you put, let me see, when you put the one only, if the model was significant. When you put the one only, it was, yeah, it was kind of borderline again. But yeah, that's the issue, right? That's why you need to choose your model right, because I mean, different models may produce different conclusions. That is a fact. Now, from all the models we have considered here, the beta binomial model seems to be clearly our best choice, and the beta binomial model didn't produce a significant p-value for marital status. So, this is the lecture of today. So I will do a very small, a very fast summary of what we have done. We have introduced a new model now, that is a model we use when we have counts. It's like counting process. And this model is based on the Poisson distribution. The Poisson distribution is the natural choice when your outcome is a count, when you are counting the number of events in a certain time window or in certain region of space. And we introduce the models, we introduce the systematic part. What you do is you model the mean as a function of the linear predictor. You need a link function for that, or response function. The mean of the count has to be positive, so typically you use the logarithm as the link function. The logarithm of the mean, or the response function, is you exponentiate the linear predictor, and that's always positive. But you can use other links as well. So that is the systematic part, and then you model the distribution part using a Poisson distribution. And we analyze then a number. Well, if you have the model, you can use now maximum likelihood to estimate the parameters. You can use all the machinery of maximum likelihood, Wald test, score test, likelihood ratio test, all this that we saw in the first two lectures. You can use it here. And then the rest of the lecture is we saw that sometimes you may not want to model the mean, but you want to model the rate, because you may have different time windows. So you may have, is what we said, it's not the same one case in 1 year that one case in 10 years. And that's why sometimes instead of modeling the mean, you model the rate, and you do that by using an offset in your model. That part we saw it as well. But now when you're dealing with Poisson data, there are many problems that can appear. One of the problems is over dispersion and under dispersion. It's a very frequent problem, over dispersion, because Poisson is very restrictive in that way. It considers that the mean has to be exactly equal to the variance, and that is frequently not the case when you analyze real data. Typically, the variance is larger than the mean. Another problem you may get when you're dealing with counting is what we call these excesses of zeros. So your data show more observations with zero than what Poisson will actually predict. And then we have seen a number of solutions for that. For the excesses of zero, we have this zero inflated Poisson model or negative binomial model. And for the over dispersion, we saw three different approaches. Two that are quasi-parametric, if you want. One is the use of the sandwich estimator. The other one is the use of the quasi-likelihood. These two procedures, these two methodologies are like quasi-parametric in the sense that you don't need to specify the full distribution correctly, like with the Poisson model. You do need to specify the mean, the systematic part correctly. But the distribution part can be left unspecified completely, or like in, for instance, in the sandwich estimator, you just need to get them in right, or you specify the mean and the variance separately, like in quasi-likelihood. But the rest, even the variance doesn't have to be correct. The rest, you can leave it misspecified. Or if you have over dispersion, then you can use a different model. This is again completely fully parametric, is the negative binomial model. And we saw that this model actually can be derived from a Poisson model in which the mean has a distribution itself, a gamma distribution that depends on the linear predictors. And so as you can see, it's a modeling framework that have many issues, and we have proposed here a number of solutions. So what we are going to do in the next lecture is going to be a nice lecture, because all the pieces are going to fall into place. So since, like we have seen today, like quasi-likelihood are going to become a lot more clear. And in the next lecture, we are going to present the generalized linear model family in all generality, because what we have been doing until now is we have been studying certain members of the family in detail. These are the most widely used members. Doesn't mean that the others are not used, but these ones, Poisson, linear models, logistic models, and linear regression models are the most widely used members of the family. But then in the next lecture, we are going to present the family in full generality. And we are going to see why all these members that apparently look so different can be embedded inside a unified family. We have seen already some hints on that, like when we get the score equations, you see that whether you're in linear regression, logistic regression, or Poisson regression, the score equations are essentially the same. The only thing you change is the mu, but the rest of the equation is the same. And but in the next lecture, we are going to see why all these seemingly so different models can be embedded just in a unified framework. Well, thank you for being here, and then I will see you next week.